Oh, yeah, I think this is it. Streamed. Okay. And now I'll copy the link. Yeah. Start. Okay. By the way, how come there are less people today? How many people are gone? So, yeah.
Because the first year will not come because they have intersection class.
Oh, they were intersection class. Okay. That's
in
clear.
this.
Then should get the time change. Yeah, we can. Okay, then let's do today and hopefully it is recorded so people can see it. Okay, welcome you guys and the person here, Anish. So the goal of today is to slightly formalize the things which we said last time, to put them a bit more properly, and extend them to the other setups which I said I would do. So last time we did a very simple setup when the function belongs to this class, everything is there's no randomness, right? Yeah, we're going to do this more generally today, and yeah, so let's see how that goes. So we recall the last time we had this notion of PAC learnability. Offside hypothesis class H. Right. So let's recall that. So in that setup, if you remember, what was H? So H was some functions, some sort of functions from some x to y. And right this. Okay, so so functions. Right. So remember, our idea was to learn a function. So the idea was learn a function f from x to y. And we had some hypothesis class which said that okay, this function can be one of these functions, one of the functions in H. So H may have maybe 100 functions, and f is one of them, or maybe H is even infinite. And then you want to ask that when can we identify this function, this special function which we have f from this big large H. So when we can do that, then we say that the function is that the H is parallel. So it's parallel if we can identify f from H using only a small number of samples. Using small number of samples. So that's the intuition. Okay, and now how do we formalize this idea? So we said that okay, it's not learnable if so H is so this happens if and only if for every distribution D on on X on X of X where it's one from X. So look at any distribution like this, and look at any function. Okay, so this is for every function. Yeah. So give me any function here. I don't care which one it is, and give me any distribution D on samples. So submitting samples x comma fx, where x is from my domain capital X. We have that there exists. Okay, and for every epsilon delta, we have some sample complexity. We have some m of epsilon delta, such that if I have these many samples, this is maybe number of samples. And some algorithm, and algorithm A. This is algorithm. So that A outputs, so that A outputs some H in H after seeing n samples. And what properties should H have? So you want that H should be the same as F most of the time, so that the probability that h of x is not equal to f of x, that they're different. So again, x comes from this B, same distribution, should be less than epsilon, and this happens with probability 1 minus 1. So with probability so with high probability, with probability 1 minus delta, the outputs hypothesis is this good, which does not disagree with F too much. So this is how we define probability. And notice that yes, so H is analytical if this happens for every distribution and every function. Okay, good. So this is fine. Okay, but now there are some caveats here, which I think I slightly alluded to last time. So number one is that we have assumed that F is from H, which may not be true. So in general, maybe your F is very complex, and you cannot really model it with a simple H, with a granular H. So like I said, if your H is very large, H is to all functions, then you typically will not be able to do that. So you want to restrict H to be something which is structured, which is learnable. But then your F might not like that, because F might be slightly more tricky. So you want to allow the notion of F not being an H. So yes, so you generalize it in the following way. Allow F not being an H. That's the first way. And the second way you want to generalize it is that maybe there is really no F which is good. So like I gave the example last time, we have these fruits and you want to predict the taste of the fruit from color and hardness, right? So maybe this actually cannot be done, perhaps. But you still want to understand this problem. So modeling this as learning a fixed function is maybe not the right thing to do. So what you do instead is to say that this distribution T is not over x fx, but instead it's over x comma y. So D over x cross y. So we have some x and we have some y, but this y is not necessarily x. So for the same x, you could have two y's, and both of the y's may have non-zero mass in D. So you may have some xy1 with the probability d1 and xy2 with probability. So that's maybe one way to capture this. So maybe you think that you look at the current hardness, and while you cannot predict the taste, it actually, but maybe you can say that okay, with some probability it's going to be sweet, with some probability it's going to be bitter, based on some unknown factors which you don't know. Okay, so that is the second change you make. And here I should give some names. So this setup is called the realizable setup. So this whatever I wrote here is called the realizable setup. Like I mentioned last time. So when there is a function and that function is actually the class. And this setup where you actually allow both things. This is called the agnostic setup. So you don't, so maybe there's a function, but the function is not in the class, or maybe function does not even exist. We actually have this. So both these setups are, they're both called agnostic. And typically, you will have similar results for both of them. That's why they clump them together into one setup. Okay, so is it clear? Realizable versus agnostic. Okay. Okay, so if you have a agnostic setup, then can someone tell me how to modify this definition? So let's look at this one. So so this is the more general thing. This is more general than this, obviously. And you can probably see why. So let's focus on this one now. So can someone tell me how we modify this definition for this setup? So what changes? So so first of all, I just change this. So right here, your distribution D on x cross y. You don't write this anymore. There is a function. Right. Okay, now some samples of algorithm. That's all right. Again, you want to output some hypothesis of the seeing some samples. What changes here? So how should this change?
So I can't expect any hypothesis in which zero error for the distribution. So I do want that to be as best as possible, like as near as possible to the best hypothesis.
Yeah, exactly. Yeah, indeed. So the thing is that this hypothesis class is some structured class, right? It's not everything. But this distribution is allowed to be really everything. So maybe even the best hypothesis in H is quite bad. Yeah, because maybe your distribution is so clever. Just say this. So if you allow any distribution, then even the best hypothesis can be really bad. Okay, so it does not make sense to say that I want the error to be small because maybe even the best hypothesis has to be there. What you can hope for is to compete against the best hypothesis in H. So you want to output a hypothesis so that this hypothesis is competitive in a small error if you compare it against the best possible hypothesis. So what does that mean? So you want to say that the error of this hypothesis with respect to D is smaller than the smallest possible error. So min H prime in H of error of H prime with respect to D plus so that's the only thing we can go for. The one thing I haven't said here is what is error. So can someone tell me what error should be? So I have a hypothesis and I have this distribution on input output. So what should the error be? So I want to see how well this hypothesis captures the input-output relationship given by me.
So is this still a classification problem? Like, is this being wired discrete?
Not necessarily, could be whatever. But okay, maybe it is just it. Yeah, so any idea? Okay, here is one way. So you just say that this is okay. So yeah, so one way is to define loss actually. So you do it in 2 steps. Oh, okay. Maybe let's first look at the case when it's discrete. The discrete then it's easy. Yeah. So okay. So if it's discrete, then what? Then it's the same thing, right? Then it's just the okay. So you look at the expectation that you sample xy from D and look at the random variable. The indicator of the random variable h of x, not a variable. Could define it like this. Or you could, yeah. So either you want to do it like this, or you want to do it with probability, which is the same thing. Also like that. That's like more general. Probability sample x, y from B, and we have h of x. Yeah, then you write the same thing here. H prime of x. Okay, so all this works if y is discrete. So right now let's say this y is just 2 x. Let's say y is 0, 1. Yeah, it's 2 levels. I have 2 levels or maybe a finite number of levels. Okay, so that this makes sense. Good. At this point, I should make one remark that okay, can someone tell me what this should look like?
If y is 0.1, then how should that program?
No, I mean then what should this minimizer try to do? Okay, so what I want to say is that you should try to predict the one which is higher about that. So if y is 0, 1, then yeah, so for any x comma 1 and x comma 0 have two probabilities P1 P1 and 1 minus P1. So whichever is bigger, you should try to predict that. So you would do that if you were allowed every hypothesis. But here you are not every hypothesis. Only allowed hypothesis in H. So then this may not be so simple. Just to get some intuition. So yeah, so every hypothesis was allowed, and this is what you would have. Would have picked the output which is higher probability. But right now, here you're restricted to H. So maybe it's not this.
Maybe you can just write that, then we can expand that probability expands y into like into two, like there can be 2 possibilities, like y is 0 and h prime is predicting 1, and y is 1 and h prime is predicting 0. And it's going to minimize the the weighted sum of this two.
Yeah, but it's not just two things now. So now you have to sum over all pairs, x over y, not just one guy. Right? So okay, so what is this really? Let's write that. So this is just sum over all x, y, and you can try integral. If it's continuous, of probability okay of x and probability of y d1x, which is the same probability of x and y times indicator of h prime x. So this is what this is. Okay. So hopefully this is interpretation. Makes sense. Any questions also on these two? Great. Okay. So
hello.
I'm going to generalize this a little bit more now in two ways. Number one is that what if y is not zero? And number two is what if you don't have labels at all? What if it's unsupervised? So yeah, so in these things, okay, so yeah, so maybe I'll erase some of this.
Hello.
Generate even more now. So you want to allow y to be continuous. And yeah, and you want to allow unsupervised setup. So unsupervised means that there are no labels. Okay, so yeah. So let's look at this case first. Slightly easier to think about. So here, you have to define what's called a loss function. You will come up with what's called a loss function. So remember, our idea is to kind of measure when our prediction h of x is not equal to y. So they were discrete, then we can just ask are they the same or not. But it's not discrete, then you want to ask how far from y is h of x. So you want to select the function L of of h of x and y, which measures how far they are, and perhaps this is, for example, this would be the square function h of x minus y squared. Okay, yeah. So and we come with lots of functions like this. So, but this may be the simplest. Okay, so yeah, so we have deal with some loss now. And yeah, so okay, so yeah, so we're dealing with some probability under some loss. So under loss L. So it's a real function from x cross y, x cross y to other derivatives. Here's some loss function now. Hey. Okay. And so here, instead of probability, what should I have? Expected loss. Expectation of loss of Hx. And same goes here. Okay. Yeah, so good. Any questions about this one? Yeah, so one example of this setup, perhaps the most famous example, is called the regression setup. So maybe you want to predict some line. So you have some points here. So maybe you have some kind of function which looks like a line. So you see samples like this. There's input, is output. And you see samples which are kind of like a line, and you want to find the best fit line. So for this input, you predict this point. And this thing here, so this loss function is saying that I measure this distance and I square that. Yeah, so this is for regression. We're linear relation is the line. So that's the most famous example of this. Yeah, and I'm sure you've seen this in many places. In school, you did some voltage versus current experiment, Ohm's law. So, probably did something like this. Good. Okay. Okay, great. So this is easy. Now, how about this unsupervised setup? They don't have it. So, so this is very weird now, because now it's not very clear what hypothesis even means. So earlier hypothesis is a function from x to y. But okay, so let's say an example. So let's say you have some data and you want to cluster it. So maybe you see samples like this. So you see samples like this, and you want to ideally predict that you have one cluster here and one cluster. So now they do that. Labels we just take samples from your domain. And your output here is a clustering. So your H here, capital H here, is the set of possible clusterings. So H is maybe all clusterings using perhaps 2 clusters. So generally we don't even know number of clusters. But let's say for now there are 2 clusters separated. And then you have some loss which you want to measure. So for any clustering, you have an idea of how bad this clustering is. And this badness can be measured in a lot of ways. So maybe you want to look at the center of every cluster, and you want to see how far these points are. So these points in the cluster are very far from the center. Then the clustering is likely not good. So maybe if you had a bad clustering, okay, what's a bad clustering? So maybe you did something like this. You instead of making these clusters, you clustered in this very weird. So then, if I look at the center of this cluster, center is somewhere here. Then the points are really far away from the center. So maybe that's a measure of how bad the cluster is. So generally, you have some notion of badness, which may not be this. So you can define a loss function on your hypothesis. So you have some loss function L, and Okay, our hypothesis is H. And what does this loss function depend on? Now you have to be slightly careful. So here we just said that you sample one point, you sample one xy and you have this loss. Here it's not so easy. Here maybe to even define this loss function to look at a lot of complicated things. So what is okay, so what is H here? When I say all clusterings, what do I mean by all clusterings? So it's really actually all clustering algorithms. Remember here, what is H here? So H is outputting a function. So H is not a single classification. H is telling me that for every point x, I should classify it like this. Yeah. So here, yeah. So I'm not inputting one point. So I'm kind of telling you the clustering label of every single point in your space. So you have this entire space which contains lots of points. And what is some H in H telling you? H is telling you that okay, this point is in this cluster, this point is in this cluster. That's what it is. Yes, yeah. So in this case, so that is this. Yeah, okay, but it's again about clustering, but in general you could have all kinds of weird tasks. Maybe you want to reduce the dimension of the input. Maybe you want to map every point. Maybe this point lives in 100 dimensions, and this H here maps this 100-dimensional point to a 5-dimensional point. So you could have maybe 10-dimensionality reduction. Yeah. So yeah. So again, it's some mapping, and then the dimensional reduction also satisfies some properties, and then you want to ask that how well does H do the properties which you want the dimensional reduction. Yeah. So we give some loss there. The point is that this loss can look very crazy. There's no simple way of saying it's not a square or anything. It could be very weird. Okay. And in particular, this loss does not depend on just one point. That's it. So like here, it doesn't depend on just one single point label. Here the loss of a point, here the loss of H would be partitioned into losses of all the different points. The partitioning I could separate the loss of. But here the separation is not possible. Similarly, dimensional reduction is not about how you reduce the dimension of one point. It's about how you reduce the dimension of the entire data set. So yeah, so really this loss is a function of H itself. So okay, so what you want to say here is that after seeing these M samples, let's call them S. So, some sample that output is hypothesis H. And I want to ask that the expected loss of H should be at most expected loss over H prime H. So now this is expectation. Here is some loss. And now this loss function is no longer from x cross y to r plus, because we're no longer talking about functions like this. Now it's just any function from okay. So now what is H? H now is any okay, so it's a function from so x and outputs something. dot for some z. So here, okay, not x to z. Okay, I think this is fine. It's just that you not define this z a bit more carefully. So z is not labels now, but here z is maybe the name of the cluster. Or here maybe it's the new point to which you have to do the reduction. So you have something like this, and then and then when you define a loss, it's no longer from x cross y to r plus, but it's from x cross the z. To r plus. Actually, not even it's because that might be very complicated. So it's like as a here's L of h. So here you want to say that it's something like okay, so to look at maybe all functions from x to z and whatever to r plus. So not loss, not the losses of the entire function itself. Yeah. Basically, so you have something like this, and okay, now a distribution on just the data. Now there's no labels. So yeah, we data just this so you sample data, and yeah, and now you have expectation of the loss of my hypothesis. Yeah, this would be at most the best possible loss from a hypothesis class plus some. Okay, by the way, this all agnostic. There is no. Okay, so this is very what we have defined. Any questions about this? So all we did is that we generalized the notion of a loss. So first our loss was just the probability. We got a loss when h of x was not equal to y. If we had functions which are discrete, then we said that okay, if we have continuous y's, then we have to define as a loss on some loss function, which is maybe a square function between the true output and your output. Okay, yeah, and then you put that your loss here, then your error here, and but then maybe you return it given unsupervised. So then maybe your loss is very complicated. Then loss depends on every point and not just pairs of points, not just pairs of input outputs. Then you talk a loss of an you talk about the loss of an entire hypothesis. So then the loss function is a function from so remember your hypothesis is now taking the data, taking your domain and outputting something z. Yeah, that could be whatever. So maybe it's cluster labels or it's some reduced dimension. And then your loss depends on the entire function, not just you just separate the loss out anymore. So maybe you can, but yeah, not always possible. So it's some loss from your function itself to r plus and then the same thing.
So here, this L of h, this is a random quantity, or L of h is depending on the sample as well.
Yeah, exactly. So that's what. Yeah. So this would depend on the sample, and maybe the algorithm is randomized also. So yeah, but yeah, it definitely depends on the sample. So very about h of s.
So h of s is the clustering of the, and L of h of s is a random error from the sample s. by some algorithm in the class.
Yeah. Yeah, so the deal is that this error, right? This error is now over every point, not necessarily over the samples. So you just saw a few samples, but maybe you actually have a lot more points, and this here is the total error. Error even over points which you have not seen.
And the right side of that is like minimum of L of X. So that is also a random quantity, right?
This is not random. See, because capital H is some fixed class which we're talking about.
Yeah.
So look at every function in that class. For every function, look at how much loss it inverts over the entire set X. Right. So maybe for reservoir clustering again. So we have a lot of possible clusterings. Let's say that a clustering can be of these different types. You look at the best one of them, the best according to maybe this measure which I said. Look at how far the thing is.
So the best one among all this clustering, that can also depend on the sample.
Oh yeah, of course, yeah. That depends on the sample. Yeah. So, okay, sure. Yeah. So this all depends on the certain prediction. So yeah, depends on what samples it is. So you have this, and this is what is next to. So you sample some.
Why are we taking these expectations like in both sides? I mean, we can also say in this way, right? That the clustering that has been picked up by the algorithm over this sample S is close to the best clustering over this sample with high probability. That is, I mean, if we say that L of HS is less than equal to mean of L of H prime S or H prime S H plus epsilon with high probability. So,
Sorry, I'm slightly confused. Can you repeat your question?
so why are we taking it's like so what delta is coming in this thing?
Okay.
Yeah.
What is delta?
Yeah.
Okay, so actually same reason as I said last time. So remember, what do you want to do, right? You want to somehow learn the correct cluster in some sense. But maybe the samples you see are very unlucky. So maybe all of these M samples are not coming from this red cluster. So in that case, there is no hope of winning. So you have to allow some probability, some little probability that you will fail completely. And then you say that so we remove that probability. And now with the remaining high probability, you want to say that the expectation of so the expected loss here. Okay. So what do you expected loss here? This is also weird, right? Because what is the expectation over now? Because the set S I have already captured here, so should not capture it again. So so this expectation is really about so let's say this particular example of clustering. So maybe I say that let me so let me sample a lot of points from distribution D. So what does a lot of points mean? So it means that maybe for every point here I assign a weight. That weight is its probability value in the distribution. And then when I measure the quality of a cluster, I give those weights to the points. So let's look at this particular measure. So what's the clustering measure here? Okay, so let's do it. Part here. So just measure the quality of a clustering quality. Clustering lost. So this is maybe saying that okay, so your hypothesis was outputting some two clusters, maybe two cluster centers, and if it was mapping every point to one of the centers, right? So maybe H here maps X to a center. And maybe this clustering loss is now the sum over all points over for all X and X. Probability of X under D times this error times the distance of X from each of X. Maybe square of this. So maybe this is your loss. So yeah, so I don't need to weight every point by the probability that it occurs at my sample. So that weighting has to somehow be done. So here we do it in this way. So this expectation here is over this weighting. Yeah, so this is not over this over these samples. So, yeah, so this and this have nothing to do with it. Okay, good. Okay, great. By the way, this is also separable in some sense, right? So here you could have done that. Here, what you could have done is we have called this the loss. So this here is some loss function L from from X to this Z. So Z here is your output. X is a point. So yeah, so here you could have done. Here you could have done this in a separate way. But okay, I think you. Good. Okay, so so this kind of the most general way of defining pathology. The agnostic case and maybe it's not even supervised. This is how you put it. Take a quick break.
only the সাড়ে সাতটায় উঠি তারও আগে আমি 6:30টায় উঠতাম উঠতে ভালো লাগতো সকালবেলায় যাচ্ছে কিছু
না না ঠিক হয়ে আমাকে কি ওই পিয়ানোটা তো নিয়ে একটু বিচার করে না আজকে সময় হাতটা বানাবো একটা লস ফাংশন আছে আমি এটা দুটো পার্সেন্টের মধ্যে ডিসটেন্স শর্টেস্ট ডিসটেন্স থেকে আছে জানেন না
By the way, so if you have dimensionality reduction, then it would not be separable typically. So what happens in dimensionality reduction? So you want to map points to lower dimension by maybe trying to preserve pairwise distances. So you want to maybe map. So in dimensionality reduction, you want to maybe map. You come with an h from x to some z. The z has lower dimension than x. So maybe you are from r to the 100 to r to the 10. R2. Map 2D, and you want to preserve distances. So you want to say that if I have 2 points, x1 and x2, in here, then h of x1 and h of x2. So the distance between x1 and x2 and h of x1 and h of x2 should be roughly the same. So you want to kind of do that. So you want that, yeah. So maybe your loss here is now the difference between these distances. So now you still have this expectation, fine, because different pairs x1 x2 will be sampled with different properties. So yes, you still have that, but now you want to say that but now your loss here depends on both the 2 points. So where x1 is mapped, where x2 is mapped are both important and not just. So now you can no longer separate it out like this. Yeah. So you can't separate it out like this. However, this notion of sampling from distribution is still there, because you want to give more importance to x1, x2, which is sampled with hyperbole. So yeah, so this definition is still kind of works, but you cannot separate it. Okay. Okay, so with all this in mind, now let's try to do some theorems about these things. Okay, so remember last time we proved that if h is finite and you're in the case when it's realizable. So h is finite and you're realizable, and your loss function is just your loss function is for finite classification. So class. So previously we did that h finite is realizable. And y is binary. Then you can learn with how many samples? The samples look something like another epsilon log h over delta. Okay, so today we want to make this a bit more general. The same thing, but with non-realizable. So we will prove that we want again h finite, h is finite. Y is still binary. But we have non-realizable. So let's try to figure this out. And again, I want to prove that this is the. So remember, what do I have to show for learnability? I have to show that there's some algorithm which, after seeing some m samples, we're seeing some m data samples, outputs a good edge. Yeah, and again, remember we have some restriction in our heads. Okay, so what's the algorithm again? Can someone tell me?
So, for one each, so it will see for every hypothesis in this class.
Yeah.
which I think
Yeah, so for every hypothesis, what will it say?
it will simply see that empirical error.
Very well. Yeah, okay. Yeah. So here's the algorithm. So output the edge in edge, which minimizes the error that you see on the samples. So a sample, a sample of the samples for errors. And what to minimize what quantity? The average. So 1 over n. Expectation. No, expectation. Sorry. The indicator that which affects is not good. The label is.
Some of the indicators.
Oh yeah, okay. This. Yeah, overall x, y, x. And more generally, if you had, yeah, so here the losses are binary. If they were not binary, then what would you do? This is not binary. Then I would take the loss. So I have some loss now. Which affects. Okay, great. Yeah, so we minimize this. Yeah, and some loss function and matrix. For agnostic. Okay, great. Yeah, so again, just quickly want to minimize this. Good, and I want to hope that this is good enough. Yeah, if that is large. So how will I do that? So again, remember last time we had a notion of a misleading sample set. So let's do it like that. So again, let's say that S is misleading. Or write down as let's call it. Let's write it in the other way around. Instead of misleading, let's call it S is epsilon representative. So that's the opposite of misleading. Representative for H if actually yeah, not your file, this is for yeah, in general, not for H. If for every okay, so it's a bunch, okay, that's it. If for every function H, the empirical error, so let's call this let's call it ls of H. ls of H, this empirical error is close to the true error. So for D of H. So that's the error under D.
There exists actually.
No, for every H. So I want to say that, okay, so I want to say that my set S does not mislead me for any H. So it means that, so give me any hypothesis in my class H. I want to say that what I see empirically, this error, and the actual error, which is this guy, they're not very far. So it's like the opposite of state. It's kind of, so any S is helping me understand what the real error is within this epsilon state. Okay. No, this is, let's say, for every H. And then what you want to prove is that the S which is sample is going to be epsilon representative with that probability. Yeah, so okay, but before that, let's just make a simple statement. We also did last time that if if S is epsilon by 2 representative, then this algorithm A, then like this one, then you are okay. So let's call this HS, right? HS, then HS is very good means that there is a closure. So let's first prove this like a simple lemma. So yeah, so remember what do I have to show that the loss of HS under D is small, right? So what is the expected loss of H of X? One X y sample from it. So we want this to be small compared to the best possible loss. So okay, so this is what we call as DH. This is DH by definition. Yeah, so we call this DH here in case of this. And okay, so the point is simply that look, D in of HS is close to erase of H. Okay, I think this is yeah. So this minus LS of HS is small. Right? This is a epsilon by because this is representative. And then the same thing about the best hypothesis. So there's some X star, which is the best hypothesis in H. So now since it is representative for every H in your H, but you also have that D L of H star. So the true error of H star minus the empirical error of H star are close. And then you just use triangle error. So these two are close. Right, and now you know that since you looked at the minimizer.
Yes.
So you know that LS of HS is at most LS of H star. So this is at most this. And then by this triangle inequality, these two have to be no more than epsilon. So this, and decide it down. LS of HS. By the way, can the guy? Okay. Is there an issue with the camera? Oh, you can't speak.
The camera needs to be turned to a
Hey,
little left side. Hello.
Hello. So which part can you not see? This side or this side? The left side. This side. Okay. Okay. See this side first. Yeah. Sorry about that. I already saw this thing now. Let me try to change the camera a bit. Oh, I think I know the problem. So this is picking this camera. I think now you can see. Okay, great. Yeah, sorry about that. Okay, so yeah, LS of this is at most LS of X star. Yeah, so combine these two and you get that this is this is the epsilon. Yeah, so combine all this and you get that D of L. Okay, I know D of L of HS. D of L of X star. So these three things will be this. Okay. Good. The upshot is that I can now stop worrying about my HS. I can just forget about HS. I have to just prove that the probability 1 minus delta, my sample S will be epsilon representative. So this is also the proof which we did last time, but yeah, maybe this is a bit more fun. Okay, so let's try to prove that now. Based on this. So yeah, so I will just prove that there is probability for delta if you have the right number of samples. Okay, if S is at least m epsilon delta. So I have not told you what m epsilon delta is yet, but we will figure this out later. Epsilon delta. S is epsilon delta. This is all you want. And you want to find this m epsilon delta for which this becomes true. That's the goal. Okay, so let's prove this, and by proving it, we'll figure out what m should be. I haven't told you what m is, so it's not proof yet, but it will become proof. Okay. Okay. So let's try to do the same kind of argument. So what's going on? So remember. Okay. So this is what epsilon representative means. Says that for every h in capital H, my loss on S and the loss of the overall distribution are not very different. So once again, I want to use union bound. So the hope is that you fix a particular edge. So you fix one particular edge. And then you define this event EH. EH is that S is not actually representative for H. EH is the event that LS of H minus DLH are bigger. I want to show that this event happens with small probability. And then, okay, so with this setup, you will have that probability that S is not absolute representative will be at most union, okay, not the probability of union or all H, right? And hopefully, and then hope is that this will be at most size of H. There are some finite number of elements in capital H, so size of H times some probability, some bound on, yeah, yes, so this is some upper bound on probability of H. So that's, and you want this to be at most delta. And the idea is that this upper bound will now depend on M. So the bigger M you have, the less likely EH becomes. So some upper bound which is decreasing in M, and from this you'll figure out what M is. That's it. From this equation, this is inequality. Okay, so that's the plan. So now the goal is to upper bound EH, upper bound this. This is the only thing that we have. Okay. Any questions about this? So we are focusing on one particular direction. Okay, so now let's ask ourselves how we about this. So what does EH happen? EH happens when your empirical average over these M samples is called. So when does EH your so let's think of it like this, that I'm tossing a coin. So doing some coin tosses. And so what's a coin toss? A coin toss is like measuring. So coin toss is like saying that I figure out L of which is like on some sample X. So my coin here is the sample X. So that's my coin. And when I toss a coin, I see head or tail. So the head or tail that I see is like this mouse. So this is what I observe. So yeah, so I see head tail, and yeah, here I see this mouse. Yeah, so that's like this, yeah, right here. And now the hope is that so if I toss a lot of coins, then the average head tail value converges to like a half. Okay, so if I toss a lot of coins, then the average number of heads will be roughly half the number of coins. And this will happen with high probability. Sorry?
It's law.
Yeah, lot large numbers, right? If you have to toss a coin 9 times, and yeah, fraction of heads will converge to half with very high probability. And I want to say the same thing here. I'm tossing m coins now, so I'm taking m samples. and I'm looking at LSH here is the average number of heads I got, or yeah, the average loss I got. So getting a head is like losing. So this is like the average loss I got. And I want to say that with high probability, this average loss converges to the true expected loss, or in the point case it was like half the number of points. So that's why this should happen. That's why this upper bound should decay very rapidly with m. Just like the expected fraction of heads converges to half very rapidly as m increases. Similarly, the expected empirical loss will converge to the true loss very rapidly as m increases. And so you get a very fast decaying upper bound here, and that should give you some good bound samples. So yeah, that's really all there is to it. The only thing that is left is to figure out how rapidly this should decay. So yeah, that's the only question. Question is how rapidly does the distribution of LSH converge. So yeah, so that's really the only thing. Yeah. Okay. So at this point, I should remind you of, yeah, I think what we already said, law of large numbers. Or maybe here you want to look at a more quantitative, stronger form, which is called the center limit theorem. So so have you guys seen the center limit theorem something? So what's the center limit theorem? Let's call it CLT. This is reminding. So yeah, who knows CLT?
So given
IID sequence.
So it is 1 by square root of n times the 1 by square root of n times the square root of n times the empirical mean minus the mean is converging to n0 or in the distribution.
Yeah, but okay, so great. Yeah, so I'm going to say a slightly more easier form of that, easier to write form of that. It's just saying that look. So, okay, so I sample, so I have a sequence x1 is x1 of IID random variables, right? And then remember here I want to understand the mean, right? So look at the mean of the instance. So xi and the idea is that this looks something like a Gaussian. So this distribution looks something like so distribution of this of this random variable looks something like this Gaussian. When the root by e to the minus x minus mu square by 2 sigma square, where sigma is the mean of the sigma square is the variance of this value.
There will be sigma outside also.
1 by square root of pi. 1 by square root of pi.
Oh yeah, sorry. Sigma. Okay, so where what is sigma square? Sigma square is the variance of this one. Where sigma square is variance of 1 over n. And xi, which is what? So remember these things are identical. So this is so the variance adds up. So this is so this is actually 1 over n times variance.
Because 1 over n square is because of the scaling element. So n times variance.
Okay, yes. Oh.
So yeah, so this is really the key punchline, that the variance of the overall random variable is 1 over n times the variance of 1. So yeah, so this 1 over n is the magic trick which happens. So that's why when you said your thing, when it's a root n, that root n comes from this. So in particular, this variance was, let's say, sigma 1, then here you would have sigma 1 square times n. Right. The sigma 1 square is the variance of itself. And here you have corresponding thing. Sigma 1 and root n. Yeah. Yeah, so then when you said you put a root n, wait, something is wrong. That's correct. Yeah, so then it looks like this. Good. Okay, so the punchline is that, okay, so let's think of sigma 1 as some constant, right? Some fixed thing which depends on the x. So the point is that you should expect a dependency of the form e to the minus epsilon square n.
Variance of epsilon is sigma 1 as sigma 1 square.
Oh yeah, sorry. Okay, yeah. So the point is that this quantity looks something like e to the minus epsilon square n. The epsilon is the difference between x and y. Epsilon is x minus. No, sigma is not gone. So I absorb the sigma in the sigma 1 by root n.
Okay.
So sigma square is sigma 1 square by n. I absorbed it. So epsilon is difference between this x. So this is an x now. Yeah, so this same with x in case this is. Okay, so this is x. Yeah, so the distribution of this random variable x looks something like this. Yeah, and here is error is so or maybe more simply this, where epsilon is the error between the difference between x and its. So what's mu here? Mu is the mean of any x. Okay, so is it looks good? Okay, so so the trouble of course here is that in this theorem holds in the limit. So I'm saying that this distribution converges to this distribution, but converges how fast is not clear. Maybe this only happens for like extremely large. But here, when you want to make a statement, you want to make a statement for some finite values of n. Here m is not any infinity. You want some bounded n in terms of epsilon and delta. So you want some quantitative version of this theorem. So what a version, you want to say that for a finite n, what kind of what will this distribution look like? So for finite values of m, and of course this take it to, but it turns out that this kind of decay is actually correct. So this is So even though I don't prove it, but this is actually correct. So this bond concentration, yes, you have seen it before. So let me state that theorem now. So I erase this. So so there is dependency remains true even for small values like a finite. Can I state that? Okay. So remember what we care about here is the probability that x minus mu. So the average you see of over m samples and the true average is far. So it's called a tail term. So if I were to plot, so if I were to plot the distribution of LSH, so here's let's say LSH. Its mean will be DLH. Yeah. So mean of LSH is DLH. And the distribution will look something like this. Right? And then you want to bound the probability that LSH is far from the mean. So maybe it's epsilon far. This is epsilon. To find the area here. Maybe the area here. So this is the area you're interested in. Okay, so here we call upon what's called Hupton's bound, which is this is for quantitative theory. So it says that if I have a bunch of random variables, so again IIT variables. Actually, here you don't even need them to be identical. I mean, you need them to be independent, but not necessarily identical. So you just need independent actually. So I have independent variables. XL. There's n of these. Maybe sorry, n. Okay, m of these. And this is the same m. M variables like this, and let me tell you that they're bounded. So let's tell you that each xi is between some di and di. Then the probability that their sum, that their average deviates from their mean. By too much. Obviously, this is bigger than epsilon. Is at most 2 times e to the minus by 2 minus where the mu is the mean. Mu is okay. So this is like very close to your CRT kind of dependence. You have this epsilon square m factor. So we had CRT, and this thing is like your variance. So variance of some n variables is like some of the variances, and b minus e s square is like some part of the variance of the variance. Yeah, so essentially this is the same. Okay, so now we just plug this thing here, and okay, so I think there's some mistake. I think there should be an m square. Because okay, yeah, so I think there should be an m square here. Because so the variance of these n variables. So when you just want some what about like e to the minus x minus c square by 2 sigma square, right? Where sigma square is the variance of this thing. The variance of this thing will be
So the comes up and
it is an m square. I just check actually. Put the cheat a bit. I think it's correct, but just check. Yeah, I think it's fine. Yeah, so you just plug that in and now you're at it. Yeah, so again, so you don't have to memorize any of this. We just remember this. Just see your thing. So you get a variance here. The variance should look like this, and this epsilon is this side. And then there's some constants which you don't care. Okay, so yeah, so I just plug it here, so I get yeah, so okay, so I get that yeah, so after I have something. So what is x side here? So x side here is what is x side? So it's a random variable a of h of x side and y. That's x side. And let's assume that the losses are bounded. So if I assume that yeah, that losses are bounded and or bounded losses are in 0, 1. And yeah, and then you have that. Yeah, then these things are all bounded, like 1. Yeah. And then you have that probability that this event happens, probability of pH. My happening is at most what? 2 the minus yeah, sorry. 2 square by 2n. And yeah, this n cancels off. Yeah, this is at most. You want it to be at most delta, and that gives you a good bound n. So n is at least. It works as whenever I use it. Oh, yeah, there's an edge. So this is for 1 and you want an h times this should be at most delta. This should be at most delta by h. So it should be at most. It should be at least. It's a similar kind of thing, but you get an epsilon square. Epsilon square log. It's a word. There's a 2. Where does 2 is?
so it's like 2 by epsilon square log.
Yeah, you get 2 is better.
So in that case, it was 1 by epsilon.
Yeah, so the thing is that you get an additional square, and you get it because it's not agnostic. I mean it's not divisible, it's agnostic. So you will incur a parallel path. That's the value. Need more samples if you don't know. If you don't know that f is in function is in the class H, and you have this agnostic case, then you will be. That's it. Okay.